Interpreting results. Modeling equation may predict impossible results. This is true for the Streeter-Phelps model. For example, if the deficit calculated from Streeter-Phelps DO sag equation is greater than the DO saturation, the result will be a negative number, because it is physically impossible for the DO to be less than zero. This means that all the oxygen was depleted at some point upstream and the DO is zero. Assuming your calculations are correct, you must use your engineering judgment and report it as zero because it cannot be less than zero. In some instances, there may not be a sag in the DO downstream. The lowest DO may occur in the mixing zone. In these instances, critical point equation will not give a useful value. TMBL mass loading. To use the DO sag equation as presented here, the mass loading must be converted to a concentration. As noted earlier in this chapter, TMBL calculations are based on mass loading. Following a general approach for calculating concentration from mass flow, we divide the mass flow by the flow of the water carrying the waste. Mass flow of ultimate BOD is equal to flow of water carrying waste. The mass discharge units are then converted to milligram per day and the water flow rate to liter per day so that the days cancel. Management strategy. The beginning point for water quality management in rivers using the DO sag curve is to determine the minimum DO concentration that will protect the aquatic life in the stream. This value, called the DO standard, is generally to protect the most sensitive species that exist or could exist in the particular river. For a known waste discharge and a known set of river characteristics, the DO sag equation can be solved to find the DO at the critical point. If this value is higher than the standard, the stream can adequately assimilate the waste. If the DO at the critical point is less than the standard, then additional waste treatment is needed. Nitrogenous BOD. Nitrogenous BOD can be incorporated into the DO sag curve by adding an additional term to Streeter-Phelps DO sag equation. Other factors affecting DO levels in rivers. The classical DO sag curve assumes that there is only one point source discharge of waste into the river. In reality, this is rarely the case. Multiple point sources can be handled by dividing the river up into reaches with a point source at the head of each reach. A reach is a length of river specified by the engineer on the basis of its homogeneity, that is, channel shape, bottom composition, slope, and so forth. Some rivers contain large deposits of organic matter in the sediments. These can be natural deposits of leaves and dead aquatic plants or can be sludge deposits from wastewaters receiving little or no treatment. Aquatic plants can also have a substantial effect on DO levels. Effect of nutrients on water quality in rivers. Although oxygen-demanding wastes are most important river pollutants on an overall basis, nutrients can also contribute to deteriorating water quality in rivers by causing excessive plant growth. Some plant growth is desirable, since plants form the base of the food chain and thus support the animal community. However, excessive plant growth can create a number of undesirable conditions such as thick slime layers on rocks and dense growths of aquatic weeds. Effects of nitrogen. There are three reasons why nitrogen is detrimental to a receiving body. In high concentrations, NH3N is toxic to fish. NH3 in low concentrations and NO3 serve as nutrients for excessive growth of algae. The conversion of NH4 to NO3 consumes large quantities of dissolved oxygen. Effects of phosphorus. The major deleterious effect of phosphorus is that it serves as a vital nutrient for the growth of algae. If the phosphorus availability meets the growth demands of the algae, there is an excessive production of algae. When the algae die, they become an oxygen-demanding organic material as bacteria seek to degrade them. This oxygen demand frequently overtaxes the DO supply of the water body, and and as a consequence causes fish to die. Water pollution in lakes. Oxygen-demanding wastes can also be important lake pollutants, especially when the waste is discharged to a contained area such as bay. There are special classes of lakes which are most seriously affected by other pollutants such as toxic chemicals from industrial discharges. A knowledge of lake systems is essential to an understanding of the role of phosphorus in lake pollution. The study of lakes is called limnology. This section is essentially a short course in limnology as it relates to phosphorus pollution. Stratification and turnover. Nearly all lakes in the temperate climatic zone become stratified during the summer and overturn in the fall due to changes in the water temperature that result from the annual cycle of air temperature changes. Lakes in cold climate undergo winter stratification as well. Biological zones. Lakes contain several distinct zones of biological activity, largely determined by the availability of light and oxygen. The most important biological zones shown in Figure 7.13 are the euphotic, littoral, and benthic zones. Euphotic zone is the upper layer of water which sunlight can penetrate. Plant growth occurs in this zone. Below the euphoric zone lies the profundal zone. The transition between two zones is called light compensation level. This picture shows the biological zones in a lake. Littoral zone. The shallow water near the shore in which rooted water plants can grow is called the littoral zone. The extent of the littoral zone depends on the slope of the lake bottom and the depth of the euphotic zone. The littoral zone cannot extend deeper than the euphotic zone. Benthic zone. The bottom sediments comprise the benthic zone. As organisms living in the overlying water die, they settle to the bottom where they are decomposed by organisms living in the benthic zone. Bacteria are always present. The presence of higher life forms such as worms, insects, and crustaceans depends on the availability of oxygen. Lake productivity. A lake's productivity may be determined by measuring the amount of algal growth that can be supported by the available nutrients. A more productive lake usually will have a higher fish population. The number of the most desirable fish may decline. Increased productivity generally results in reduced water quality because of undesirable changes that occur as algal growth increase. Table 7.3 shows lake classification based on productivity. Oligotrophic lakes. Oligotrophic lakes have a low level of productivity due to a severely limited supply of nutrients to support algal growth. As a result, the water is clear enough that the bottom can be seen at considerable depths. Eutrophic lakes. Eutrophic lakes have a high productivity because of an abundant supply of algal nutrients. The algae cause the water to be highly turbid, so the euphotic zone may extend only partially into the epilimnion. Highly eutrophic lakes may also have large mats of floating algae that typically impart unpleasant tastes and odors to the water. Mesotrophic lakes. Lakes which are intermediate between oligotrophic and eutrophic are called mesotrophic. Although substantial depletion of oxygen may have occurred in the hypolimnion, it remains aerobic. Senescent lakes. These are very old, shallow lakes which have thick organic sediments and rooted water plants in great abundance. These lakes will eventually become marshes. Eutrophication. Eutrophication is a natural process in which lakes gradually become shallower and more productive through the introduction and cycling of nutrients. Cultural eutrophication is caused by when human activity speeds the processes naturally occurring by increasing the rate at which sediments and nutrients are added to the lake. Thus, lake pollution can be seen as the intensification of natural process.